We'll start in a minute. Today and tomorrow, we will review for test 3. We'll go over the test 3 review sheet as much as we can anyway. So in number 1, identify the curves in the XY plane represented by the parametric equations and indicate the direction that the curve is traced as t increases. Then eliminate the parameter t and write an equation in terms of x and y. So for this one, x equals 2 times sine of t, y equals 3 times cosine of t, and t ranges from 0 to 2 pi. So if we put in a few t values, the main ones like 0, pi over 2, pi, 3 pi over 2, and 2 pi, and then find the x and y coordinates. When t is 0, the x coordinate is 0 because sine of 0 is 0, and the y coordinate is 3. When t is pi over 2, 2 times sine of pi over 2 is 2 for the x coordinate. 3 times cosine of pi over 2 is 0. And at pi, sine of pi is 0, so the x-coordinate is 0. 3 times cosine of pi is negative 3. When t is 3 pi over 2, sine of 3 pi over 2 is negative 1, so 2 times negative 1 is negative 2 for x. Cosine of 3 pi over 2 is 0. So 0 for y. Then when t is 2 pi, sine of 2 pi is 0. The x-coordinate is 0. Cosine of 2 pi is 1, so 3 times 1 is 3. Then if we plot those points in the xy plane, so when t is 0, the x-coordinate is 0 and the y-coordinate is 3. So we get the ordered pair of 0, 3. Then at pi over 2, the x-coordinate is 2. The y-coordinate is 0. Then we have the ordered pair of 0, negative 3. The ordered pair negative 2, 0. And then 0, 3 again. So the initial point and the terminal point are the same point, but the curve, the direction is clockwise. So this is a rough sketch. So do you recognize that figure or what it's supposed to be? It's an ellipse. That's what it's supposed to be, an ellipse. Then we eliminate the parameter t. So any suggestions on how to eliminate the parameter t? Well, I'll just rewrite those equations. X equals 2 times sine of t, and y equals 3 times cosine of t. On this equation, I'll divide both sides by 2, so I get x over 2 equals sine of t. On this one, divide both sides by 3, so y over 3 equals cosine of t. Then if we square each side of those equations, square the left-hand side of this equation, we get x squared over 4 equals sine of t squared. Square both sides of the other equation, we get y squared over 9 equals cosine of t squared. Then if we add the equations, so add the left-hand sides, x squared over 4 plus y squared over 9 equals the sum of the right-hand sides, sine of t squared plus cosine of t squared. But sine of t squared plus cosine of t squared equals 1. So we get the equation of an ellipse. X squared over 4 plus y squared over 9 equals 1. Okay, the next one, part B. X equals e to the t and y equals e to the negative 2t. And t ranges from negative infinity to positive infinity. So note that the x coordinates for all values of t are positive. E to the t is always positive. And e to the negative 2t is also always positive. So the x and y coordinates are never 0 and never negative. Well, one strategy for picking t values let's start with a negative value like the natural log of 1/10. The natural log of 1/10 is negative. Well, I'm picking the natural log of 1/10 to use as my t value because e to the natural log of 1/10 is just 1/10, right? And then you can think of y as, instead of e to the negative 2t, you can think of that as 1 over e to the 2t, or perhaps even better, think of that as 1 over e to the t all squared. Do you agree with that? This is just a strategy to employ. You don't have to do it this way. But since I know that e to the t is 1/10, then 1 over 1/10 is 10, and 10 to the second is 100. So that gives us an idea. When x is small, a small positive number, 1/10, the y value is pretty big. So the next t value I'll pick is the natural log of 1, which is 0. And so e to the natural log of 1 is just e to the 0 or 1. And the y coordinate is 1 over 1 to the second, which is also 1. And let's just pick one more t value. This time I'll pick the natural log of 10. And e to the natural log of 10 for x gives us 10. And for the y value, what's the y coordinate that goes with that? 1 over 100, yeah. If e to the t is 10, we have 1/10 to the second, or 1/100th. Okay, so we can sort of get an idea of the graph. So x is always positive. Y is always positive. When x is 1/10, the y value is off the grid. So the y-axis is a vertical asymptote. So as the t-values increase, the direction of the curve is downward. So the graph will look something like this. Okay, to remove the parameter t, this is pretty simple. Since x equals e to the t, and you can think of y as the quantity 1 over e to the t to the second, you can start by writing y is equal to 1 over x to the second. All I did was replace e to the t with x. And this is perhaps not the most conventional way, so you can rewrite 1 over x squared as y equals 1 over x squared. The domain is x greater than 0 because the way the parametric equations are defined, x has to be positive. Okay, the next problem, number 2, write parametric equations for the line in the xy plane that passes through the points 2, 1 and -1, -3. If we focus on the x coordinates, then the parametric equation for x as a function of t, one way to do it is to multiply the x coordinate 2 by the quantity 1 minus t. And then add the quantity t times the x coordinate of the other point, which is -1. And then do the arithmetic. So we get 2 minus 2t minus t, or 2 minus 3t. So we can check. The idea here is when t equals 0, I'm at this x coordinate. So when t is 0, my x coordinate is 2. And then when t is positive 1, I'm at the other x coordinate, -1. So when t is positive 1, 2 minus 3 is -1. So that works out. Right, this equation for x, this parametric equation for x, gets me from the x coordinate 2 to the x coordinate -1 on the interval from 0 to 1, when the t values are from 0 to 1. Then we do the same thing for the y coordinates. Multiply the y coordinate 1 by 1 minus t. Then we add that to t times the y coordinate of the other point, which is -3. Then do the arithmetic. 1 minus t times 1 is 1 minus t, and plus -3t is minus 3t. So the parametric equation for y is 1 minus 4t. For the entire line that passes through those 2 points, we have to let t be any real number. Okay, and number 3, find an equation of the line tangent to the curve x equals t to the second minus 1 and y equals t to the third plus t, corresponding to t equals 2. Okay, so in order to find an equation of a particular tangent line, we need to know 2 things. We need to know the ordered pair of the point that the tangent line passes through. And we also need to know what the slope of that line is. And if we have those two, if we know those 2 things, we can write down an equation for that line. So let's first find the point, the x and y coordinates that correspond to t equals 2. So x is a function of t. We want to evaluate that function when t equals 2. So we get 2 to the second minus 1, or 3 for the x coordinate. And then evaluate the function y of t when t equals 2. And we get 2 to the third plus 2, which is 10. So the point on the curve through which the tangent line is going to pass is the ordered pair 310 for x and y. Okay, now we want to find the slope of that line. So we need the derivative. We need to find the derivative of y with respect to x. And then find the slope of the line. Well, y is a function of t, so dy dx, remember, is dy dt in the numerator and dx dt in the denominator. So the derivative of y with respect to t in the numerator is 3t to the second plus 1. And the derivative of x with respect to t in the denominator is 2t. And then the derivative of y with respect to x is a function of t. And we want to know what that value is when t equals 2. So this might seem a little weird, but I'm going to write dy dx as a function of t, and we want to evaluate this when t equals 2. Okay, so in the numerator, 3 times 2 to the second plus 1 is 13. And in the denominator, 2 times 2 is 4. So this is the slope of the tangent line that passes through the point 310. So now we can just write down the equation. We can start with the point slope form. So y minus y1 equals m times the quantity x minus x1. So y minus 10. And then the slope is 13/4. So y minus 10 equals 13/4 times the quantity x minus 3. And that is a good enough equation if you want to leave it just like that. Okay, the next page, number 4, find the area enclosed. So find the area enclosed by the curve x equals t to the fourth minus 4 and y equals t to the third minus 2t for values of t between negative square root of 2 and positive square root of 2. So let's get an idea of what the curve looks like. So I'll pick t values, negative square root of 2, negative 1, 0, positive 1, and positive square root of 2. Okay, when t is negative square root of 2 for x, when we raise that to the fourth power, we're going to get 4. And then 4 minus 4 is 0 for x. And then the y-coordinate, so we're going to get the number negative square root of 2 to the third minus 2 times negative square root of 2. We also get 0 for that. Then when t is negative 1, negative 1 to the fourth is 1, and 1 minus 4 is negative 3. And then for the y-coordinate, negative 1 to the third is negative 1 minus negative 2 is negative 3 plus 2. Oh, sorry. So negative 1 to the third is negative 1. Oh, and then plus negative 2, we get positive 1 for y. Is that right? Is that what you got? Okay, then when t is 0, the x-coordinate is 0 minus 4 or negative 4, and the y-coordinate is 0. And then when t is 1, we get negative 3 for x, and 1 minus 2 is negative 1 for y. And then when t is the square root of 2, we're going to get 0, 0 again. So let's plot the x and y coordinates. The smallest x coordinate is negative 4. So we have the point 0, 0, negative 3, 1, negative 4, 0, negative 3, negative 1, and 0, 0. So it forms a type of loop, something like that. Okay, so to find the area that's enclosed, remember the formula. If you have parametric equations, x equals f of t and y equals g of t, then the area is going to be from, well, here's the formula, from alpha to beta of g of t times f prime of t dt, where g of t is y, so y equals g of t, and x equals f of t. Okay, I'll point out something. Notice that when x ranges from 0 to -4, the t-values range from -√2 to 0. So if we want to get a positive number for the area, we have to evaluate this integral from the √2 to the -√2. You might remember when we talked about the orientation of a curve. If the x values are in reverse order to the ordinary order of the t values, then the resulting integral will be negative. So if you want it to be positive, you switch the order of integration. But even if you don't catch that, in the end, you just take the absolute value of the number that you get. Okay, so our g of t is t to the third minus 2t. And then dx dt is 4t to the third. So I'll just take this one a couple of steps further because the integral is pretty easy to evaluate. So our integrand is 4t to the sixth minus 8t to the fourth dt. So the antiderivative will be 4/7 times t to the seventh minus 8/5 times t to the fourth from the √2 up to -√2. So I'll leave the rest of that for you to work out. Okay, on the next one, find the arc length of the curve x equals t to the second and y equals t to the third minus t over 3 for values of t between 1 and 3. Okay, so on this one, what's the formula for arc length for parametric curve?
Dx over dt squared, like the square root of dx over dt squared plus dy over dt squared.
Yeah, it's the definite integral of the square root of dx dt squared plus dy dt squared dt. Is that what you said? Yep. Okay, so x is t to the second. So dx dt is 2t. Y is t to the third minus t over 3. So dy dt is 3t to the second minus 1/3. And then we're going to square both of those and then add them, then put them inside the square root. So maybe, since we're squaring 3t to the second minus 1/3, if we write that as a single rational expression, it might help. Maybe it will make it more complicated, but I'm going to rewrite 3t to the second minus 1/3 as 9t to the second minus 1 all over 3. And then when we square both sides, dx dt squared, and then plus dy dt squared. We can do it all at once, maybe. When we square dx dt, we get 4t to the second. And then when we square 9t to the second minus 1 over 3, in the numerator, we'll get 81t to the fourth minus 18t to the second plus 1 over 9. And then a common denominator is 9, so 4t to the second will become 36t to the second over 9, and we'll put it all in the same rational expression. So 36t to the second plus 81t to the fourth minus 18t to the second plus 1. And then combine like terms in the numerator. We get 81t to the fourth plus 18t to the second plus 1 over 9. And both the numerator and denominator are perfect squares. So that's going to be pretty nice because they're going to go inside of a square root. So let's write the numerator as 9t to the second plus 1 quantity squared over 3 squared. Hey, this is going to go inside the square root. I guess I'll try to squeeze it in. So the t values range from 1 to 3, so we have the square root of the perfect square. I'll just write all of this as 9t to the second plus 1 over 3, all squared. So we get a simple integral to evaluate. We get just 9t to the second plus 1 over 3 dt. So I ran out of room, but this is pretty easy to evaluate. So I'll leave that for you to do. Okay, and the next one, find the surface area generated by rotating the parametric curve about the x-axis. Okay, so x is t plus 1, y is equal to t minus 1 over 2. T ranges from 1 to 5. So the surface area formula for this, say from alpha to beta, is 2 times pi times our g of t. Our g of t is what y is equal to. Or you could just write y, but I'll go ahead and write g of t. And then multiplied by the square root of dx dt squared plus dy dt squared. Okay, that's our surface area formula for parametric curves if it's rotated about the x-axis. So we might as well focus on dx dt squared plus dy dt squared first. Dx dt is just 1. dy dt is 1/2. So when we square those and add them, one squared plus 1/2 squared is 5/4. So that's the number that goes inside the square root. Okay, so our surface area, as t ranges from 1 to 5, is 2 pi times t minus 1 over 2. That's the g of t, times the square root of 5/4 dt. So I'll just take this a couple of steps further. These, we can cancel those twos, 2 divided by 2. And we'll bring the constants out front. So the square root of 5/4 is the square root of 5 over 2 times pi. Square root of 5 over 2 times pi. And then the integral from 1 to 5 of the quantity t minus 1 dt. Okay, the rest of that is pretty simple. So I'll leave the rest of that for you to do. Okay, sketch the following curves. So r equals sine of 2 theta. So what's it going to look like? Or what are we going to get? I know it's hard for you to read my mind when I ask those kinds of questions, but there are going to be loops. How many? 4 loops, yeah. I mentioned this before, so I'll write it in a little more detail. If you have r equals a times sine of n theta, or r equals a times cosine of n theta, if in either case, if n is an even integer, then there are 2 times n loops. And if n is odd, how many loops are there? N. Yeah, so if n is odd, there are n loops. So in this case, n equals 2, so there are going to be 2 times 2 loops, or 4 loops. Okay, if we sketch the Cartesian equation first, then since it's sine of 2 theta, one period of that will be from 0 to pi, and the second period will be from pi to 2 pi. So I'll go ahead and try not to write too small, I guess, but so 2 periods will occur between 0 and 2 pi. So the length of each subinterval is pi over 4. So I'll try to squeeze those in. So can you see my microscopic writing? So the 2 periods look like this. So then when we're just using this as an aid to draw the polar curve. Okay, so I'll put these dashed lines where this one is theta equals pi over 4. This one is theta equals 3 pi over 4. Okay, so starting at 0, r is 0 when theta is 0. When theta is pi over 4, the r value is 1. So that's the first half of the first loop. Then between pi over 4 and pi over 2, the other half of the loop, we go back to 0 at pi over 2. So this is the other half of the first loop. Okay, then between pi over 2 and 3 pi over this is supposed to be 3 pi over 4, sorry. Between pi over 2 and 3 pi over 4, the r values are negative. So where's the loop going to be? It's going to be opposite of this sector, so it's going to be in this sector. So sometimes I have to reorient myself here. So between pi over 2 and 3 pi over 4, so yeah, it's going to be down here. And then from 3 pi over 4 to pi, we go back to 0 to complete the loop. So those loops are supposed to be the same shape and size, but mine aren't, but they're supposed to be. Okay, between pi and 5 pi over 4, the r values are positive, so we're making our loop in that sector. And then from pi over 4 to 3 pi over 2, the r values go to 0, so we're completing that loop. And then between 3 pi over 2 and 7 pi over 4, the r values are negative. So the loop has to be in the opposite sector, so it's going to be up here. And then from 7 pi over 4 to 2 pi, in the opposite sector, since the r values are negative, we end up like that. So hopefully you get the idea of how that works on that one. Okay, on the next page, we have some other parametric curves. So on this one, r equals 1 minus cosine of theta. So first, we'll sketch the Cartesian graph. So one period will be from 0 to 2 pi this time. Okay, when theta is 0, cosine of 0 is 1. 1 minus 1 is 0. Then cosine of pi is 0. Sorry, cosine of pi over 2 is 0. 1 minus 0 is 0. Cosine of pi is -1. 1 minus -1 is 2. So the first part of this will look something like this. Then cosine of 3 pi over 2 is 0. 1 minus 0 is 1. And then 2 pi, cosine of 2 pi is 1. 1 minus 1 is 0. So we get this curve. This is the Cartesian graph. Then the polar curve. So what did you get for a polar curve? When theta is 0, r is 0, so the first point is at the origin. At pi over 2, the r value is 1. So pi over 2, we're on the positive vertical axis. Between 0 and pi over 2, the r values are pretty short, and then they jump to 1 all of a sudden. So the r values are pretty short. Then between pi over 2 and pi, the r values range from 1 to 2. So we get something like this. Between pi and 3 pi over 2, the r values go from 2 to 1. And then from 3 pi over 2 to 2 pi, the r values go back to 0. So this is supposed to be a cardioid. Okay, what about the next one? R equals 2 times cosine of theta. We've seen this, maybe not this one in particular, we might have, but what is it?
A circle
Yeah, it's just a circle.
with radius 2.
Yeah, the radius is 1.5, centered at 1.5, 0. But we have a few minutes. Let's go ahead and first draw the Cartesian graph. So it's just r equals 2 times cosine theta. So we get a 1 cycle between 0 and 2 pi. Okay, so the graph will look in the Cartesian graph looks like this. And then the polar curve. When theta is 0, the r value is 2. By the time we get to pi over 2, the r value is 0. But I think what I said earlier is incorrect. But so let's put in an intermediate value. Let's see. Cosine of pi over 3 is 1/2. 2 times 1/2 is 1. So that looks about right. And then between pi over 2 and pi, the r values are negative. So the graph will be in the fourth quadrant over here. And then between pi and 3 pi over 2, the r values are negative, but it just retraces the circle. So that's supposed to be a circle. Since there's less than a minute, let's convert this to an equation in x and y. So how would we start if we want to convert r equals 2 times cosine of theta to an equation in x and y?
R is equal to x squared plus y squared? Or r
Yeah,
squared?
r squared is. So what we can do is we can multiply both sides by r to get r squared equals 2 times r cosine theta. And then r squared is x squared plus y squared. R times cosine of theta is x, so this is equal to 2x. And if you want to take it a little further, you can write it as x squared minus 2x plus y squared equals 0. Complete the square on x squared minus 2x by adding 1 to both sides. And then you get the standard equation of a circle, x minus 1 squared plus y squared equals 1. So this verifies that it's supposed to be a circle. But that's all we have time for today. We'll continue the test 3 review sheet tomorrow.